In this lecture, we will be looking at integrals of vector-valued functions. So recall, a vector-valued function, r of t, is defined by these components, f of t, g of t, h of t, on a domain D, and it's a rule that assigns this vector in space to each element t in D. And we can think of it as the position vector that points to a particle as it traces out the trajectory along a space curve. Now, we looked at taking derivatives of vector-valued functions, but we can also go the other way and integrate vector-valued functions. So let's look at the indefinite integral of our vector-valued function r of t with domain D. And our integral is defined in the following way. So the indefinite integral of r of t dt is capital R of t plus c, where capital R of t is any antiderivative of little r of t, and c is a constant. But this capital R of t is a vector. This capital C is a vector. And the way we can think of it is here, the antiderivative or indefinite integral of little r of t. To get that, we take the regular antiderivatives, as we learned in single variable calculus, of each of the components. So for instance, if we wanted to look at this r of t equals cosine of t, sine of t, t, and we wanted to take its indefinite integral, we can integrate each of the components. So we have the integral of cosine of t dt, and then the integral of sine of t dt, and the integral of t dt. And we can do each of these as we have when we learned integral calculus. So antiderivative of cosine of t will be sine of t plus, say, c1. Antiderivative of sine of t would be minus cosine of t plus a constant, say, c2. And then the integral of t dt would be t squared over 2 plus c3. And we can see we can break this up into the sum of vectors sine t minus cosine t, t squared over 2 plus c1, c2, c3. And in this way, this would be our capital of r of t plus our constant vector c. We can also talk about definite integrals. So let's again consider our vector-valued function r of t. And suppose its components are integrable on the interval ab for t. Then so is r of t. And the definite integral of r from a to b is, we write it in the usual way, integral from a to b of r of t dt is this here. And we see that we do the ordinary definite integral for single variable calculus inside each of the components. So, for example, the same question. We have the integral from 0 to pi of r of t dt. We integrate each of the components, integral 0 to pi of cosine of t dt, integral from 0 to pi of sine of t dt, integral from 0 to pi of t dt, and we can use our fundamental theorem of calculus with an antiderivative. So we'll have sine of t between 0 and pi, and of course any antiderivative works for the definite integral, so we choose the one where the constant is c1 from before is 0. Then we have minus cosine of t evaluated between 0 and pi, and t squared over 2 evaluated between 0 and pi. And we get, for the first component, sine pi minus sine 0. For the second component, minus cosine of pi minus a minus cosine of 0. And for the last component, pi squared over 2 minus 0 squared over 2. Sine of pi and sine of 0 are both 0. Cosine of pi is a minus 1. So this is a minus minus 1. Minus minus cosine of 0. Cosine of 0 is 1, so that's plus 1. Pi squared over 2. So we get 0, 2, pi squared over 2. We can also construct these initial value problems because just like we have in single variable calculus, if we integrate, we come up with an arbitrary constant, and we need initial values to tie those down. So in this case here, we are given an acceleration vector, an initial condition on the velocity, an initial condition on the position, and we want to find that position vector r of t. So first, we know that v of t is our antiderivative of acceleration. In this case, this is the antiderivative of 0, 0, minus 32. And we can rewrite that as the integral of 0 dt, the integral of 0 dt, the integral of minus 32 dt, which we know is 0 plus c1, 0 plus c2, minus 32t plus c3. We now want to lock down that constant, so we note, using this, that if we plug in t equals 0, v of 0 is c1, c2, minus 32 times 0 plus c3, or c1, c2, c3. From our initial condition, v of 0 also must be equal to 50, 50, 0. And these two must be the same. From our initial condition, we know that v0 must be 50, 50, 0. And these two are both different versions of v0 and must be the same. Thus, c1 is 50, c2 is 50, c3 is 0 when we match the components of these vectors. And so that gives us that our velocity vector is equal to, coming back here, 50, 50, minus 32t. To get the position vector, we now integrate the velocity vector with respect to t, and we do this again component-wise. So we have the integral of 50 dt, integral of 50 dt, integral of minus 32t dt, which gives us 50t plus constant, say, d1, 50t plus constant, say, d2, minus 32t squared over 2 plus d3. And we can use this, as we did before, to say that r of 0 has to be what we get if we plug 0 in for t here, which would be d1, d2, d3. But r of 0 also has to be the initial condition we were given, which is 0, 0, 100, and we can equate the components to conclude D1 is 0, D2 is 0, D3 is 100. And so we can plug those back in here. We'll get 50t minus 16t squared plus 100, which we see depicted here. Now, one question is, what is this scenario? We were just given this initial value problem with this constant acceleration, and recall we had V naught was 50, 50, 0, and R naught was 0, 0, 100. Well, if you think of R naught as our position vector, that's saying at time 0, we are at the point 0, 0, 100. V0, 50, 50, 0, you can think of that. So if we draw that vector, we would go 50 along the x-axis, 50 along the y-axis, and we would get a vector that looks like this. But now let's take that vector. Remember, its direction and magnitude is what matters. We can move it anywhere. So let's move that velocity vector, v0, up here. And so we have this scenario. And then our acceleration, 0, 0, minus 32. This, if we think in feet for our x, y, and z, and t, we think in seconds, what we have is an acceleration due to gravity scenario. So that acceleration vector being 0, 0, minus 32, this gives us the constant acceleration in the negative z direction. Due to gravity. Our initial condition R naught, that's our initial position. So we can think of it as we're standing atop a 100-foot cliff or a 100-foot building. V naught is our initial velocity. And so it's like we're throwing a ball or a rock off of the top of a 100-foot building. It's being thrown in this direction. The speed, right, so the initial speed is the magnitude of that velocity vector, which is the square root of 50 squared plus 50 squared, which is root 2500 plus 2500, or root 5000, which we can write as root 50 times 100, or 10 root 50. 50 is 25 times 2, so we have 50 root 2. So 50 root 2 feet per second is our initial speed at which this thing is thrown off. In this direction, right, right into the first octant from that building 100 feet high. And then because of acceleration, our r of t, our position vector, the acceleration due to gravity, will give us a trajectory downward like this. So after the ball is initially thrown, gravity is bringing it down. So this is an example of an initial value problem. You could have been given this either way. Here we were given it where we were given the acceleration vector and initial conditions and asked to interpret it. But you also could be asked this question in the other direction, where you could be given the question, you're standing atop a 100-foot building, you throw your ball in this manner, and you have acceleration due to gravity, ignoring air resistance, and what is your position vector going to look like? But the point here to see is that we can do integrals in a very similar way to how we do them when we first learned basic integral calculus. And that same is true for initial value problems.